Welcome to this video on specific heat capacity for GCSE Physics. We will cover the core concepts, the necessary calculations, and how to approach the required practical and exam questions. In this video, we will explore what specific heat capacity means, the units and key quantities involved, how to use the equation with confidence, the steps for the required practical, and essential tips for exam success. Have you ever noticed that a frying pan heats up almost instantly, while the water inside takes much longer? This difference is due to a fundamental property called specific heat capacity. Understanding this concept is essential for physics and has real-world applications in cooking, engineering, and climate science. Specific heat capacity is defined as the amount of energy required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. It is represented by the symbol C. A higher value means the material needs more energy to heat up and will also release more energy as it cools. Materials with a high specific heat capacity, like water, heat up and cool down slowly, making them useful as thermal stores or coolants. Conversely, materials with a low specific heat capacity, like copper, heat up and cool down quickly, which is useful when rapid heating is required. Water has one of the highest specific heat capacities of any common substance. This property is vital in the real world. The sea acts as a massive heat store that moderates coastal climates, water serves as a coolant in machinery, and it efficiently distributes heat in central heating systems. There are 3 key quantities to track: energy, measured in joules, mass, which must be in kilograms, and temperature change, measured in degrees Celsius or Kelvin. Always remember to convert grams to kilograms before starting your calculations. Here is a summary of the units at a glance. Energy Q is in joules, mass M is in kilograms, specific heat capacity C is in joules per kilogram degree Celsius, and temperature change is in degrees Celsius or Kelvin. These are all linked by a single equation. The specific heat capacity equation is Q equals M times C times change in temperature. This links the thermal energy transferred to the material's mass, its specific heat capacity, and the resulting change in temperature. To solve physics problems, you must be able to rearrange this equation. Depending on what you need to find, you can calculate energy, the specific heat capacity, or the temperature change by rearranging the variables accordingly. Let's look at an example. To find the energy needed to heat 2 kilograms of water from 20 to 70 degrees, we identify our values and apply the equation. By multiplying 2 kilograms by 4,200 and the 50-degree temperature change, we find we need 420,000 joules. For our next example, we need to find the specific heat capacity of a metal block. We rearrange the equation to isolate C, substituting the energy of 9,750 joules, the mass of 0.5 kilograms, and a 30-degree temperature rise gives us a specific heat capacity of 650 joules per kilogram degree Celsius. In the required practical, you will determine the specific heat capacity of a solid block. You do this by supplying a known amount of electrical energy using an immersion heater and carefully measuring the resulting increase in the block's temperature. The essential equipment includes an electronic balance to measure mass, a thermometer to track temperature changes, a power supply and joule meter to measure the energy supplied, and a stopwatch to control the timing of the experiment. The method is straightforward. Weigh the block in kilograms, record the starting temperature, heat the block for a measured time while recording the energy used, and finally, note the highest temperature reached after switching off the heater. To complete the calculation, first record the energy from your joule meter. Next, determine the temperature change by subtracting the initial reading from the final. Apply these values to the equation, and finally, check your calculated specific heat capacity against known databook values to assess your accuracy. If you are using a voltmeter and ammeter instead of a joule meter, you can calculate energy electrically using the formula Q equals V times I times T. You will measure voltage in volts, current in amps, and time in seconds. Then substitute this value of Q into the specific heat capacity equation. Reliability is key in science. A single run can be prone to random errors. To improve your findings, repeat the experiment at least 3 times to calculate a mean. Use insulation to reduce heat loss, ensure good thermal contact, and use a digital thermometer for more precise readings. Be aware of common sources of error. Heat loss to surroundings can lead to an inaccurately high value for specific heat capacity. Poor thermometer placement causes reading errors, while failing to account for the block continuing to absorb heat after the heater is switched off can result in a lower final temperature reading. Why repeat the experiment? Repetition is essential for scientific reliability. It allows you to identify anomalous results, calculate a more accurate mean, reduce the impact of random errors, and demonstrate reproducibility. Always mention repeating and averaging if asked how to improve an experiment in your exam. This table shows common materials and their specific heat capacities. Notably, water's value is roughly 10 times higher than most metals, which explains why water is such an effective coolant and heat storage medium. This chart highlights water's exceptionally high specific heat capacity compared to metals. It illustrates that for a given amount of energy input, lead will heat up much more rapidly than water. Central heating systems utilize water's high specific heat capacity. Because water can store a large amount of thermal energy per kilogram, a relatively small volume can efficiently transfer heat throughout a building. If water had a lower capacity, radiators would need to be much larger or operate at higher temperatures. In engine cooling systems, water-based coolant absorbs enormous amounts of heat from the engine block. Thanks to water's high specific heat capacity, it can absorb this energy without its own temperature rising too dramatically, effectively preventing the engine from overheating. Coastal climates are often milder, because the sea heats up and cools down more slowly than the land due to water's high specific heat capacity. This buffers temperatures, whereas inland areas far from the sea experience more extreme seasonal swings. Substances with higher specific heat capacities make better thermal stores. Water, at 4,200 joules per kilogram degrees Celsius, is an excellent choice for heating systems, while metals like aluminium and copper, with much lower values, are better suited for applications needing fast heat transfer. Remember this key exam principle. The greater the specific heat capacity, the more energy is needed to achieve the same temperature increase. Materials with a higher C value require more energy, while those with a lower C require less. This is why metals heat up faster than water. In this multiple-choice example, we compare two blocks of equal mass. Block A has a specific heat capacity of 500, while Block B has 1,000. Block A will show a greater temperature increase because it has the lower capacity, requiring less energy to heat up. For calculations, always show you're working. In this example, we calculate the energy required to heat 1.5 kilograms of water by 82 degrees. By multiplying the mass, the specific heat capacity of 4,200, and the temperature change, we reach 517,200 joules. When describing the practical method in an exam, follow this framework. State the required measurements like mass and temperature, describe the procedure using a heater and joule meter, show the calculation using the standard formula, and always explain how to improve reliability through repetition and installation. Let's cover some common exam mistakes. First, always convert grams to kilograms, because 1 gram is 0.001 kilograms. Using grams will result in an answer that is 1,000 times larger than it should be. Secondly, ensure you calculate the change in temperature, represented by delta theta, which is the final temperature minus the initial temperature. Never use the final temperature alone, as that will lead to an incorrect result. Thirdly, don't confuse high and low specific heat capacity values. A high value means a substance heats up slowly and requires more energy, while a low value means it heats up quickly. Be sure not to mix these up in your exam. It is crucial to distinguish between temperature change and temperature itself. The equation uses delta theta, the difference between the final and initial temperatures. For example, a shift from 20 to 80 degrees Celsius is a change of 60 degrees. Students often confuse specific heat capacity with specific latent heat. Remember, specific heat capacity applies when the temperature is changing while the state remains constant. Specific latent heat applies during a state change, like melting or boiling, where the temperature stays constant. A heating curve shows temperature over time. The rising sections represent periods where specific heat capacity applies as the temperature increases. The flat sections indicate state changes, such as melting or boiling, where the temperature remains constant and latent heat is involved. When performing the practical, remember that energy is conserved. While electrical energy is supplied by a heater, some is inevitably lost to the surroundings as thermal energy. This is a key principle in understanding why measured results may vary from accepted values. Your calculated value for specific heat capacity is often higher than the accepted value because of heat loss to the surroundings. Because the block absorbs less energy than the joule meter records, the math produces an inflated value for circa wrap your block in insulation to improve your results. Here is a quick summary of the key facts. Specific heat capacity is the energy to raise 1 kilogram by 1 degree Celsius, calculated with the equation Q equals mc delta theta. Its units are joules per kilogram degree Celsius, and you improve reliability by repeating the experiment and calculating a mean. Finally, use this checklist to prepare for your exam. Can you state the definition, use and rearrange the equation, describe the practical, and explain errors and improvements? If you can cover these points, you are ready for your exam. Good luck!